Of course, a special thank goes to our keynote speaker of this year's Embedded World. It is not a secret that artificial intelligence continues to change the world at a rapid pace. From the embedded viewpoint, we don't see only AI in the cloud, in the backend, in the big servers, but also at the edge, distributed. I repeat myself when I'm mentioning that the predecessor of Embedded World back in the 1990s was called Embedded Intelligence. At that time, this was a dream. Now we are somewhat there. A story with an open end. We should remember that we are just in the early days. In order to take a deeper look into this process, we are proud and honored to have Rich Simoncic as our keynote speaker for this year's Embedded World. Rich joined Microchip in 1989 and became COO in April 2024. He oversees Microchip's worldwide operations and is leading the company's AI-related effort. He founded Microchip's internal analog business in 1998, growing it to over $2 billion in annual revenue. Rich previously held roles as Executive Vice President, Senior Vice President, and Vice President. He holds a Bachelor of Sciences in Electrical Engineering Technology from the Free Institute of Technology. For his keynote, he selected a very nice metaphor, learning from the octopus, nature's blueprint for intelligence everywhere, where an octopus had 2/3 of its neurons being distributed throughout its tentacles and skin, enabling each to sense, decide, and act independently. But I don't want to tell your story and invite you to the stage. Let us receive Rich with a warm applause. Thank you.
Hi. Hey, thanks, Axel. I don't want to spill this all over the electronics. I could just see Alex get all upset here. Well, good morning. It's interesting. I don't know what everyone has their morning rituals, right? My morning ritual is to get up, open up YouTube, and see what's new in the world, in news. So I open it up, and the first thing I get hit with is a commercial for a solar panel. And the company formed this flower or solar panel, and they based it on a sunflower. They watched how a sunflower opens up its petals with the sun in the morning, and then the sunflower turns throughout the day, and then at the end of the day closes down. And so they based their entire solar panel on what a sunflower does. So in a way, that's what we're here to talk about with an octopus. So first of all, I'm honored to be here, giving a keynote at Embedded World, the leading trade council for embedded design. And yes, Axel slipped me some money to say that this morning. So nature's blueprint. And let's get this going here. You'll notice that I really love octopus, and in fact, AI really loves octopi as well. So there's a lot of hype about autonomous AI, on the edge and physical AI. A lot of it is alien to most of us. The thought that a non-living system can make its own decisions feels like science fiction. So perhaps we may need to look at the nature for some understanding about autonomous AI. So in nature, there is one animal that can help us understand autonomous AI. Today, we're going to talk about the octopus. And I'll start by giving you a few facts to ponder about an octopus. An octopus has 9 brains, a central brain, and each 8 tentacles has a brain of its own. Essentially, 2/3 of an octopus's neurons is distributed throughout its body, allowing the octopus's 8 legs to act independently. Perhaps 3 searches for food, 2 scans the bottom, and 3 are used for movement. Could you just imagine having 8 legs as an octopus and going, how many did breakfast brunch this morning? You could have 1 leg getting coffee, 1 leg getting a pretzel, 1 leg getting some sausage, all the while 2 legs are walking you through the line. That's essentially what an octopus does on a daily basis in terms of searching for food and moving around. An octopus has blue blood because it's copper-based and not red like us because it's iron-based. And that allows it to adapt to low oxygen and cold environments. Each part of an octopus has independent optical sensors and allows it to camouflage itself instantaneously as it crawls across the bottom. In fact, you know what? I would love to have that ability today. As soon as you walk into the Hall 4A, the first thing you're greeted with is the ST microelectronics booth. And me being from Microchip, I would love to walk into that booth and all of a sudden my Microchip badge changes to ST and I walk in there and I could learn everything that ST is working on. And then I could walk right next door to the NXP booth. My badge changes to NXP and I could see what's going on and listen into conversations on every one of my competitors as I walk through the hall. That's essentially what an octopus can do. An octopus, as it crawls along the bottom, it automatically changes camouflage color based on the environment without talking to the central brain. An octopus even has 3 hearts. Has 1 for the body and 2 for the gills. Even an octopus's genetic code is more complex than that of a human being. An octopus has 33,000 genes, 13,000 more than a human being. So an octopus is fascinating and genetically advanced animal, and it can really help us understand the autonomous edge. So 2/3 of an octopus's neurons are distributed throughout its tentacles and skin, enabling each to sense, decide, and act independently, while the central brain sets goals and coordinates that activity. The octopus has developed an evolutionary strategy for intelligence that is both resilient and efficient. Let's imagine an octopus investigating, let's say, a crab trap or a jar. It will send its arms to probe different parts at the same time. One arm feel for the opening, another tests the lid, another braces the object, and yet another arm explores inside. The distributed intelligence that is in each arm locally processes both touch, taste. They have the chemoreceptors and the suckers, the texture and the grips, and movement on the fly without needing step-by-step instructions from the brain. The brain provides central orchestration and sets the goal. Open this, get food, decides when to switch strategies, and coordinates overall posture and effort, while the arms handle all of the micro decisions. Why this is so very, very, very cool and relevant, it's like 8 semi-autonomous sub-processes running in parallel under one high-level objective. In the embedded world, we have long recognized the value of distributed intelligence, and the octopus metaphor reflects intelligence pushed to the autonomous edge, where sensing, decision-making, and action occur locally instead of through a centralized brain, or other words, an MCU, MPU, FPGA, CPU, or GPU. Just like how an octopus arms can function and react independently from its central brain, distributed AI and autonomous edge is not about making edge devices smarter than the cloud. It's about making systems more resilient, efficient, and trustworthy by embedded intelligence where action happens. Distributed autonomous AI doesn't require every node to be cloud-level smart. It requires fast local inference, deterministic responses, and energy efficiency. Verification, authentication, and being tamper-resistant at that edge. Learning updates without humans in the loop. The model aligns with the core principles of distributed systems: integration of sensing, control, and compute at the edge, low power, deterministic operation rather than brute force compute, and autonomous subsystems that operate reliably even when disconnected. In essence, distributed autonomous intelligent architectures build the tentacles or arms in a hardware system, much like an octopus. So if autonomous intelligent architectures build the tentacles or arms in a hardware system like that of an octopus, it's more about resiliency and efficiency rather than raw intelligence, which would then lead us to framing of distributed AI as reflexive intelligence at the edge, coordinated but not controlled by the main system. In practice, this means nodes perform narrow, task-specific inference, decisions are made locally whenever possible, and only summaries or exceptions or learning updates are propagated upward. This type of model is ideal for industrial automation, automotive subsystems, smart energy and infrastructure, medical, and safety-critical devices. Despite the hype, the truth is not everything AI has to be big and flashy. Edge AI excels at handling straightforward, practical tasks using machine learning and MOPS, GOPS, and yes, eventually TOPS ranges. So sitting down at the MOPS or GOPS level, keyword spotting, predictive maintenance, battery life improvements, object detection and negotiation, fault detection, motion detection. Many of these functions can be done on standard embedded control devices. And by integrating AI solutions, they are often performed more accurately and at much lower power and cost than previous solutions. You may also then progress to more sophisticated models for autonomous AI. Here are some cases where you'll be migrating from GOPS to TOPS: vision systems for robotics, surveillance and modern defense systems, medical imaging, autonomous vehicles, UAV, automotive, commercial transport systems. You have to really stare at this picture to notice the difference between the two octopi. Does everybody see it? Who is that person last night at dinner with the short arms? Right? Big brain, short arms, not willing to pay. So the two octopi up here are to generate the large brain, small arms, small brain, large tentacles. So power is a central challenge in AI systems and execution, but we need to look at it differently. While TOPS or GOPS are important, compute power is not always the most important variable. AI efficiency is better determined in TOPS per watt or measured in microjoules per inference. The AI model interaction is key, providing the decision-making needed in the smallest footprint possible with the least amount of power consumed. For example, in the case of the octopus above, we are looking for a big brain with little arms and tentacles, or can a smaller brain with far-reaching arms and tentacles solve the problem better? Technically, the architecture of the MCU matters the most. Memory bandwidth and the ability to fit the model, memory, to get the most performance for that particular model. Example, it's like putting Albert Einstein as the driver of a Formula One race car. He may be able to think through every scenario and every curve on the road, but will his motor skills match the demands of the racetrack? So just because you have the biggest brain is not going to make it the most efficient system. So true efficiency can be found useful in decisions per joule over the system's lifetime. So this is a kind of an interesting example. Probably not it's not the same manufacturer. So here we have a simple power drill. And you would probably say, why would I use AI in a power drill? Right? Why would I use AI in a power drill? So we had a manufacturer, we had a chip designed into a power drill, and his manufacturer wanted to know if they could put an ML algorithm on a power drill to see if they can enhance battery life. So we worked with this manufacturer. We took about 2 months to collect data on the motor and the battery, built a model for them, and in the end, wound up providing them with 15% more battery life without changing any of the hardware that they had in that particular power drill. So in other words, did not need an accelerator, did not need any fancy, huge amount of RAM. We were able to do it in less than 200K of memory, and in the end, are now shipping millions of power drills and power devices with 15% more battery life without any hardware changes. So it's not always the case of changing out this huge device to solve small problems on the edge. In fact, here's another story. I was driving through Germany a few years ago, and we broke down. And we needed one tool in our toolbox. And that one tool happened to be a screwdriver. And we failed to have the nice screwdriver in our toolbox. In 2017, when I launched Microchip going down digitization and AI and almost everything that we used at the company, I often would put a toolbox in front of the audience. And I would equate AI to as just another tool in the toolbox. And in fact, it's your screwdriver within a toolbox. So when you look at AI, it is just another tool for us to use in our toolbox. No different than Microsoft Excel, no different than your cell phone, just one more tool in the toolbox. So with autonomous edge nodes, you need AI as that tool within your toolbox. Distributed AI nodes become mostly asleep at times, awake only on relevant signals, running small models in milliseconds, returning quickly to deep sleep. The hardware technology behind solving the power challenge on the edge will need to include ultra-low power MCUs and FPGAs, integrated PMICs and analog, sleep states and wake-up event architectures, and event-driven processing instead of continuous polling. It's not just about low power or just about high performance independently. In the end, it will always come down to decisions per watt needed. This was important 20 years ago and is even better enabled using AI models on the edge today. So, conversations about AI can often sound complicated, but sometimes it is, but in reality, simplicity is crucial when scaling AI solutions to billions of connected devices across the industry. The trend is moving towards self-contained, AI-capable systems that integrate multiple functions, such as sensor interfaces, signal conditioning, lightweight machine learning inference, control loops, and security features. In fact, we found with many of our customers, about 70% of the time, we can implement an AI solution on that device with the standard product that's already designed in with merely software changes. We must meet customers by enabling smarter autonomous edge nodes and software changes first, rather than pushing major hardware changes to implement AI on the edge. Customers are asking for a tool chain that can support their development from small, non-accelerated devices to highly accelerated systems with significant TOPS. For instance, within Microchip's, one of Microchip's wafer fabs, we ran about 100 diffusion pumps using a motor wear-out system that we developed using a standard MCU. That information monitors these pumps alerts us when something is about to go bad with the pumps. It automatically sends that information to an agent. The agent automatically orders the new pump and then schedules the pump replacement in the with the manufacturing technicians without any human in the loop. That is probably going to be the way most intelligent systems work in the future. This approach reduces integration complexity, streamlines development, and enhances reliability and security for large AI deployments. For Microchip, we've been investing heavily in getting the software environment and tools right before launching multiple families of hardware. You will see more about these advances through 2026, and with the tagline, build once, scale anywhere. So please check back and look and see what advances within software we'll be releasing throughout the year. So if cybersecurity isn't always on your mind, it should be, especially with more and an increased focus on regulations like EU's Cybersecurity Resiliency Act and other standards emerging worldwide. Security threats now and in the future are highly relevant in distributed autonomous AI. Your cybersecurity infrastructure cannot be entirely cloud-based, like that of an octopus in this model. Compromising one tentacle does not compromise the system. Each node maintains its own trust and integrity. Each node can sense danger or an intrusion and act independently to block the intruder. So in an embedded system, your key security measures may include one of the following: secure boot, hardware root of trust, crypto accelerators, secure key storage, lifecycle and provisioning tools. We can also apply security to distributed AI, such as building in these system architecture attributes. Models are authenticated and versioned. Inference integrity is validated. Nodes can be revoked or isolated. Learning updates can be verified by the central brain. Can you imagine the levels of physical AI being deployed and people finding ways to disturb those devices? Humanoids, factory robotics, any physical AI product, it will be crucial to secure those devices for human safety. I think in the end, we all need to design in autonomous anti-tamper systems that doesn't rely on just centralized cybersecurity, but localized physical security. Like with an octopus, severing an arm, or think Mission Impossible and a chip going poof and erasing when physically tampered with. The most vulnerable part of a system or a nation's infrastructure is going to be the edge, where there are no guns, no guards, no fences, no gates. Just as an octopus distributes intelligence across its tentacles for resilience and efficiency, the future of embedded systems requires AI that senses, decides, and acts locally. As devices scale into the tens of billions, centralized intelligence hits limits of power, security, latency, and reliability. Edge AI gathers data and provides context back to centralized systems. They can do it through metadata, or edge nodes can do it through compressions. Autonomous edge nodes can analyze input from sensors of the real world that they're attached to, compress that data, and send it back for a structured format to a central system. I know you're all waiting for how this relates to the octopus. So an octopus can crawl over rocks while simultaneously changing color and skin texture differently across its body and arms to match the background. The distributed intelligence in the local skin and arm circuits adjust chromophores, color cells, and texture bumps across based on local visual and tactile input. Now, what is the central brain doing during all of this? It's telling it to hide, blend, or some type of threat display. It coordinates the global pattern. So why is this cool? I know you're all wondering. Well, it's the first time talking about an octopus with real-time distributed sensory motor control. Now, after looking at some octopi analogies and the intelligent edge, what we have learned is Rich has some serious octopus issues. Distributed AI is architectural, not computational. Distributed AI does not replace the cloud, but distributed AI can augment the cloud using local inference, creating a complete solution. It enables local autonomy while preserving system-level coordination. Instead, Edge AI can own how intelligence is structured in embedded systems, the standards, tools, and architectures that enable it, the power and trust envelope that makes distributed AI at scale. Not everything needs an accelerator. Not everything needs an AI ML model. Not everything needs 100 plus TOPS of processing power. Understand your decisions per watt and tune the system accordingly. First, see if you can modify the software of the current hardware and add AI without a complete redesign. And then you notice the big red eyes on this cute octopi, right? All the while keeping your mind that a security breach is your worst nightmare. So keep it secure to prevent the creatures of your nightmares from coming to life. I want to remind you that an octopus is a cute, lovable sea animal and should not be seen as a creature of your nightmares. And look at that. I've made it most of the way through this keynote with only mentioning my company's name once, but I did wear it on my shirt, until now. If I could enforce one defining principle about Microchip, it's this: build once, scale anywhere. Our autonomous edge strategy is centered on delivering a single unified tool chain that provides a complete user-centric experience, making it easier for customers to build AI directly into their hardware solutions. At Microchip, we intentionally started with the foundation, the tool chain and AI software environment first. We focused on enabling developers to be productive, scalable, and confident across MCU, MPU, and FPGA platforms. Many of you have already seen the leadership in action, beginning with our AI-enabled MCU development tools launched in February 2025, followed by AI agents introduced in September 2025, which is helping customers reduce software development time by up to 60% or more. And this is not a one-time milestone. You will see continual advances throughout 2026 as we further expand and mature this AI development ecosystem. So in closing, I want to say that today, as we scale to billions of autonomous edge connected devices, the challenges and opportunities of managing power, integration complexity, and future security threats are more relevant than ever. Let's work together from the octopus and shape the next generation of distributed autonomous edge AI to improve the human condition for a safer, smarter, and more productive world. And thank you.